Okay, so we said that when we're looking at ionic things, in this case, let's imagine we're looking at, oh, I don't know. Let's look at magnesium and some nitrogen. Okay, so when we're asked to come up with a name, right? So here I've given you the formula, right? I've told you what his chemical formula is, and your job is going to be to come up with his name. Later, we'll practice me giving you a name and coming up with the formula, but we're going to go in this direction first. There are rules to naming ionic compounds, right? So when you know the formula and you have to come up with the name, we have to figure out where the metal comes from, right, which neighborhood, and where the non-metal comes from. So as we're looking through here, we're going to ask ourselves, where does that metal come from? Remember, there are two places this metal could come from, and depending on where it's located, that's going to tell us what rule to use. The metal is either going to be main group in these two alkali-alkaline earth metal clusters, or it's going to be in the transition block or underneath of the metalloid stairs. Right? So we can see that magnesium is located in the alkali earth metals. So he is what we're going to call a main group metal. Okay, a main group metal means that the charge is fixed. Okay, so the way the charges work, this is mentioned in your textbook, but it bears mentioning now. The reason why main group ions are so much easier to deal with is because they have a fixed ionic charge. So these are going to give us a fixed ionic charge. Remember, we said we make ions when electrons either leave or when they show up, right? So if we lose electrons, we make cations. If we gain electrons, we make anions. So the cations live on this side. Everybody in group 1, even hydrogen, even though he's in a weird place, this is why he lives in group 1. Every element in group 1, when given an opportunity to take or give electrons, always lose one electron. Okay, these guys, that's what they do when they enter into chemical reactions. They lose one electron every time. They're really predictable. It's what they need to do to be stable. If they lose an electron every time, then their ionic charge is always going to be a positive 1. So that's a piece of information that you have to internalize for yourself. You're going to be expected to know that. So lithium, sodium, potassium, rubidium, cesium, francium, everybody in group 1 forms a +1 charge. Everybody in group 2 always forms a +2 charge because they are always going to lose 2 electrons, right? So everybody here is always going to be a +2. So if I ask you the ionic charge of calcium, calcium is always going to carry a +2 charge. If it's given the opportunity to gain or lose electrons, it will always lose 2. It's really predictable. The transition metals are not predictable. They're a crazy mess, and so they have transitional states. I cannot tell you their charges, right? They have various charges at various times, and so that makes them harder for us to name. We're going to save them till the end. So if I move over here, if you recall back in the first video, I said that group 1 and group 2 metals were main group metals, and then I also said, and we're going to throw in aluminum. He was the one that made the jump. Aluminum, it turns out, is a metal that always forms a +3 charge. Those are the, oh, crazy. Those are the metallic, no, apparently I can't draw 3, I don't know. Okay, I did it. All right, woo. So, it's a +3 charge on aluminum. He always forms a +3 charge. The other post-transition metals and transition metals we can't say with certainty exactly. I'll throw in some caveats to that. But those are the charges that you have to understand. While I'm here, I'll go ahead and tell you about the charges on the anions. Everybody over here in the nonmetals, okay, so I'm only talking about nonmetals here, and I'll draw a line to show you that in a second. The nonmetals over here always gain electrons, right? That's what it means to be anions. These guys are going to gain electrons. Nitrogen will always gain 3. Now it's weird because when he's gaining 3 electrons, oh no, It makes him have, no, okay, so weird. Okay, so he always carries a -3 charge, right? That counts for nitrogen and phosphorus, and we're going to consider to be true for arsenic as well. Remember, these charges only apply to the nonmetals. As soon as we move beneath arsenic, we're talking about transition metals and metalloids. So these guys don't follow the rules. These guys follow, right, the transition rules, which we're going to talk about later. So these guys are all in this big transition family, and we're going to come back and talk about that in another video. For now, we're just talking about the anions, or the nonmetals, that are of interest. So these guys always lose 3 electrons. These guys always lose 2 electrons, right, all the way down here. They will all carry a -2 charge. Everyone over here carries a -1 charge. Those are the charges that you have to memorize on the periodic table. And everyone over here carries a 0 charge. Circles. They don't want to gain any electrons, right? These guys have what we call a full octet. They're incredibly stable, and they're chemically inert. So they don't want to pick up any electrons. The reasons why these numbers are -3, -2, and -1, it shows how many electrons each elements or each group needs to gain in order to have electrons equal to, I'm scared about writing circles now. Okay, I'm going to square everything. Okay, so nitrogen has 7 electrons. If he wants to have as many electrons and feel almost as stable as neon, he has to pick up 1, 2, 3, right? So you can memorize these numbers, certainly, or you can kind of develop a deeper understanding about where they come from. So if we think about sulfur, sulfur has 16 electrons, and we want it to go along and feel about as stable as argon. And so to do that, he's at 16, and he needs 18 electrons, and that's why sulfur always undergoes chemical reactions to pick up 2 electrons. Okay, so there are the charges that you're going to be held responsible for. So take a look now. I'm about to discard all my pictures, so I'll draw them again if I ever come back to that particular image. But what that says to us is, when we go back and name magnesium, we need to know that magnesium lives here in the main group metals, so that when we come back, we're going to use the following rules. We're going to see that magnesium lives in the main group metals. His charge is fixed. It will always be +2. And because of that, we get to just give him his full name. So when we're naming the formula, we're going to give full name to the metal. So we're going to call him magnesium. That's a long-winded thing. Obviously, we call him magnesium. I went on and on about it. But when you see the metal, you go to the periodic table, you see where it lives. If it's in the main group metals, you just write his name, simple as can be, nothing else. Then we go and we look at the nonmetal, right? And we have to go figure out where the nonmetal lives. This nonmetal is not polyatomic, right? That's the important thing. Not polyatomic. If it was polyatomic, we'd go to that list that you're going to memorize, and we would look up its formula and its name. It is not polyatomic. So we go and we find his name, nitrogen. We keep the first syllable, right? We drop the ending, and we add I-D-E. So the name down here for this compound is going to be magnesium nitride, right? If I just called it magnesium nitrogen, you wouldn't know if I just had magnesium hanging out next to nitrogen or if they're bonded together. This indicates that these two guys are involved in an ionic bond. This spelling change, right, is crucial because it's telling us that he is doing something with the magnesium. It's like when we get married, although I don't because it's patriarchal and weird. I didn't change my last name, but we'll imagine that when these elements get married, someone has to change their last name so that you know that they're really married. So we see that the nonmetal undergoes a spelling change always in these binary compounds. I should probably say this somewhere. So this is how to draw binary, or rather how to write the formula and the name for binary compounds. Right? And we know it's binary because there's one kind of metal and one kind of nonmetal. Okay. So now that we've gone through one pretty slowly, the rest are going to come along pretty quickly, right? So let's imagine that I show you this guy. Right? So if we're evaluating this, we're going to ask ourselves the same set of questions. We're going to go look at the metal. We're going to find out that potassium lives here, right? Potassium's a main group metal, so we know that he just gets his normal name. So we're going to say potassium. We're going to look for sulfur. We see again that it's just one element. It is not a polyatomic. So we're going to keep the first syllable. We're going to drop the ending, right, the UR, and we're going to add IDE. So he's going to be potassium sulfide. There's my non-metal spelling change. So if I was going to make a set of rules, right, that you guys could, what does this do? No, that's not what I want. Okay, if I was going to make a set of rules that you could follow or, make a list about, the rules would look something like this for naming binary compounds. For binary compounds, when the metal is main group, you, one, write the metal name from the periodic table. Right? And then two, write the first syllable of the nonmetal plus IDE. That's it. Okay, so I'm going to throw up a couple practice problems for you to work on, and then we'll move on and we'll make a small video about how to go the other way. Okay, so that's how we're going to turn a formula into a name.